Here we're going to look at question 50 from the ENGAA 2018 paper. In this question, we're told we have a collision between a mass small m and a mass large M. We're also told that initially the mass small m is moving with a velocity u towards our mass large M, which is stationary. Then, after the collision, we're told that our mass small m is moving with a velocity v in the opposite direction to its initial direction of travel. Then, what we're asked to do is to find beta, which I've labelled here as being the velocity of our mass large M after the collision. If you would like to go ahead and have a go at this question, pause now, otherwise we're going to have a go at it. So before we begin, I think it's worth noting that here I drew a diagram to help visualise the information given in the question. And this is, in my opinion, always a good thing to do, especially with a collision question, since it's just a really concise way of putting the information that we need to know up on a page. Anyway, how could we have a go at solving this question? What methods could we use? Well, as is often the best thing to do with collision questions, we should go ahead and use conservation of momentum. So the reason we would use conservation of momentum is that energy is not always conserved in the motion of the balls or of the objects colliding in a collision. So this is quite difficult to see from our equations sometimes, and it depends on whether or not the collision's elastic or inelastic, but conservation of momentum always holds. Momentum is always going to be conserved between our objects colliding. So therefore, it's often the best thing to go ahead and try and use. Bearing that in mind, let's try and set up our equation for conservation of momentum, which is going to be that the momentum before the collision is equal to the momentum after the collision. So, the momentum before the collision is going to be the momentum of our mass small m, which is going to be small m multiplied by u, plus the momentum of our mass of large M, so large M multiplied by 0 meters per second because it's stationary. This is going to be equal to the momentum of our small ball afterwards, of mass small m, multiplied by this velocity minus v, which is negative because it's in the opposite direction to the initial direction of travel, u, which I labelled as positive. Then the momentum of the large ball of mass large M is going to be equal to m multiplied by beta. So, simplifying and rearranging this, we get that by bringing the v over onto the left-hand side and factorising our m out the front, that large M multiplied by beta is equal to small m multiplied by u plus v. We can then just divide by large M to find that beta is equal to small m multiplied by u plus v all over large M. This is going to correspond to answer E given in the question.